In this video, I want to talk about the electric field of a linear charge distribution of uniform charge density at a point P on the axis bisecting it. So that's quite a mouthful. So what am I talking about? I'm talking about a linear rod here. We assume that the width of it is negligible. So it really just has a length, and it's basically of continuous charge. So at first, when you see that, it might be a little difficult to comprehend, but you can just imagine the whole thing is charged. So the pink everywhere just represents charge. And so what the question is asking us to do, and so there's some special cases that involve the electric fields of along various axes and points due to various charge distributions. And so this is the first one that we're looking at. And so there's a few of these special cases. There's about 5 in total, including like a ring and a disc. But this is just the rod. And so this is really the first time maybe that we'll really get into the thick of some of the integration that goes on, of integrating the components and trying to find from the infinitesimal component what the total component is. So let's start by, so we want to find the total electric field vector at this point due to this linear charge distribution. So some point along this axis here that's bisecting it. So we assume that this rod here has total length of 2L. So I want to find the total electric field at P, the net electric field. So there's sort of a problem-solving strategy that we follow. So one of the first things we want to do is we want to start talking first start talking about the infinitesimal vector. So what do I mean? So if I take, let's see, a color that's more visible, I've already overused that one. So if I take a little dq, so this green area here, this green bit here, so this has charge dq. Let's start by considering what, and again, we're assuming this rod is positively charged. If it was negatively charged, then the equations we'll get in the end will just have a negative sign in the front of them in terms of direction. So anyways, so if I want to find what the electric field is due to this dq, so at point P, so if it's positive, it's going to be along here. It's going to be along this straight line, and then it's going to be this dE that comes off here. Right? And so that's the dE of this dq. This is the infinitesimal electric field vector of this infinitesimal amount of charge of our rod. So now let's imagine moving our dq along. So if we moved our dq along here, and let's say we moved it along here. So for position 2 here, and I'll do this in a different blue, we see that, you know, maybe this electric field, so it's starting to rotate a little bit to the left, so it's here, and then this one's going to be a little more, it's going to still be upwards, but to the left. And so if you imagine rotating the entire way across, the dE is going to, of this segment over here of dq, is going to be pointing all the way to the left over, well, as left as it will be for these infinitesimal vectors. And so we end up getting all of these dEs, and our goal is to add them all up. And so what we do is we start by just considering one dq, and then we start by adding it up. So let's break this dE into components. So, and let me give myself a little more room. I want to get rid of this. Let's see if I can do this without erasing something important. So that's the P. I'll draw the P a little lower. So I want to break up this dE into components. Whoops. Draw this a little shorter. So this right here is dEx. It's the x component. So if we're going to write this guy in terms of components, and so this is the general strategy, is we start by considering an infinitesimal vector due to an infinitesimal amount of charge, and then we break it up into components, and then we try to integrate each component over the entire length. And then this vertical component is going to be dEy. And this angle right here, we're going to call this theta, angle theta. So this angle right here is theta. And so we're going to, let me write the second one here. So I'm not doing a good job at color coding it, but I can at least get one of them. So the blue, blue, orange, orange, and then this should probably be green, but alas. So this is it written in components. So now and I'll start writing this guy in green just to be more clear what I'm talking about. So if I want to write this guy, if we want to write either of these, of writing it in terms of the magnitude and the angle, right? So let's say that the magnitude of this dE is, right, it's just going to be this. It's going to be dE, which we sometimes write as just this. We just write it as dE without the vector and so on. So the magnitude of this is going to be dE, so we know from just splitting a vector up into components that this guy is going to be written as dE, whoops, I don't know why I drew a dot, dE, and then it's going to be cosine of theta plus, and then the other one, which is going to be dE plus sine theta, right? And we also have to include, don't forget, the directions, right? Because we're writing it in with the magnitudes and then using the unit vectors in either direction, positive I hat, positive j hat, to write this as write these as vectors. And so one of the things that I want you to imagine is as we integrate along this rod, imagine that dE vector pivoting along point P. It starts by pointing, starts by pointing over here, and then it's going to be pointing up here, and then pointing to the side a little bit as we start getting over here. And so as you imagine that, what you see is that the horizontal components end up canceling, right? So if I add up all of the horizontal components along this rod, the horizontal components of the dEs are going to cancel. They're going to cancel each other. So by canceling, we mean they're going to end up summing to 0. This dE is going to cancel this, the dE of the dQ over here, and then if I move to this dQ, it's going to be canceled by the dE of this dQ, and if I go over here, it's going to be canceled by this one, right? Because I'd have this, and then this, and their horizontal components are going to end up canceling, right? So when I integrate this dE to find the total E, I'm actually only going to be working with the Y component. All the Y components are adding. You see that all those dE vectors point upwards, so they're all going to be adding, but the horizontal components cancel. So we're just going to actually work with the vertical components because we know we're going to be integrating, and so if we integrate this guy, this is going to end up becoming 0. So in our integral, that's just going to become 0. So we're just going to work with the Y component. So we've got our dE equals, and then we've got dE, and I don't know why this shouldn't be up. This should be more clear that this is a parenthesis and that this is another parenthesis. Sorry about that. So dE sine theta, and then in the j hat direction. So how do we rewrite dE? So we know basically what ends up happening is we treat the dQ as a point charge. So we know that the equation for the magnitude of the electric field due to a point charge is just, Coulomb's constant times the magnitude of the charge over r squared. Sometimes we write it without the absolute value bars and just remember that the Q is the magnitude of the charge. And so if I want to write this in infinitesimal form, it's just going to be dE, the infinitesimal electric field vector, times Q, times the infinitesimal amount of charge over r squared. So r in this case is the distance from here all along here to the point P. So this distance is r, right? And so first of all, let's just continue rewriting things. So first we get that this is actually k dq over r squared. Still have our sine theta. I want to try to, it takes a little bit longer when you do each step one by one, but I hope to give a more, slightly more involved so that maybe becomes more obvious or clearer at least. Now I want to deal with the sine theta. So looking at this triangle right here, so actually we'll be, so let me continue actually labeling some things. So this distance here is y, and then the distance to our dq is x. So as our dq moves along, so then x becomes on the other side of the axis. It's measured from the origin to whatever dq we have. So y is going to be a constant. So if we're looking at this triangle right here, right? So it's this, and this is a right triangle, and this is point P over here. So this is y, this is x, and then we have our blue r, right? So r, and then what is r? Well, by the Pythagorean theorem, it's going to be x squared plus y squared, right? C squared equals a squared plus b squared. So then you take the square root of both sides. C equals the square root of x of a squared plus b squared, which is just a is x and b is y here, right? So, and our angle theta is right here. So we can rewrite the sine theta as just being y over r, right? I won't sub in the Pythagorean theorem bit yet. And I'll just continue doing it in the same colors. So k dq over r squared. We rewrite the sign, so it's going to be y over r, and then j hat. Right? Maybe I'll actually leave this. Whoops, that's j hat. Okay. So now we can rewrite the r's in terms of square root of x squared plus y squared. So we do this. So let's actually, so we multiply these fractions. So we get k dq. This is going to be r cubed, and then we have our j hat. Okay, and now we're going to sub in what we know r to be, right? And so r is the square root. So I want to talk about, so r equals the square root of x squared plus y squared, which is the same thing as writing x squared plus y squared to the 1/2, right? So if I have r cubed, that's the same thing as having x squared plus y squared to the 1/2, all raised to the third, which you just multiply the powers just by exponent rules. So this becomes to the 3/2. So over here, when I sub in r and for r cubed, I'm going to end up getting x squared plus y squared to the 3/2. I don't want to forget my j hat unit vector, right? And so now you might be wondering, well, where do we go from there? So what you end up having to do, and this is sort of another general idea in these problems, is that you want to rewrite the dq in terms of charge density. So because this is linear charge density, it's a rod, there really isn't any other charge density to work with. So it's going to be lambda equals dq over, and then in the last video I talked about dl, the infinitesimal length. Well, since we're doing that length along the x-axis, it's just dx, right? And this is a uniform charge, uniformly charged rod, has uniform charge density, so we can also say q over its total length, which is 2l. So let's just take this left side. We'll work with this equation for now, right? And so we get that dq equals, if we multiply the dx over, we get this. And so if I go back to the equation I have, and I want to sub that in, so ky, and then it's going to be lambda dx, and for the dq, right? X squared plus y squared. And this might seem like a lot of arithmetic, but these special cases do follow a general pattern. So it might seem like a lot perhaps at first, but hopefully you'll get more used to it over time. And so now what we want to do is we want to find the net electric field vector at this point, right? Point P, I've drawn it in so many colors you can't hardly see it, but we want to find the net electric field vector. So that's going to be, it's going to be E, and then again, so how do I find the total of something from the infinitesimals of it, the infinitesimal amounts of it? Well, you just integrate, right? And let me continue using this greenish color. So you just integrate it, right? And so technically, if you wanted to say, you could say, yeah, okay, so it's from 0 to E, but conceptually, you're just integrating all the dE vectors, right? And so in our case, so then you're going to be integrating this right side of the equation, which is ky lambda dx over x squared plus y squared to the 3/2. And then you have your j hat vector. So I don't want to lose my picture. I don't want to get too far away, but I'm going to need more room. I don't want to get scrunched up. So this bottom part on the left becomes just a net electric field. So now we can pull. And our limits of integration. So they're going from negative L to L, right? On our drawing. If we look at this drawing, so it's going from x equals negative L to x equals L, right? So Now what we want to do is we want to pull the constants out of the integral. So what's actually changing when we do this integral? So k is Coulomb's constant. That's going to stay constant. That's not changing. The y, the distance, the perpendicular distance from the rod to the point P, that's not changing. Lambda is also not changing because we said it has a uniform charge density. The thing that's changing is x. So we can pull, and also the unit vector isn't changing. So we can pull all of these constants out, and I'm just going to write the unit vector like this now. And we're left with this integral, which unfortunately it's probably going to be one of the nastiest integrals that you have to deal with because it actually involves doing trig substitution. So the general, and I'll perhaps include another video perhaps later on how to do this integral, but you can also remember that this is an integral that appears, I don't want to say too often, but it certainly does appear somewhat. So this is to the 3/2 dx a to b. So this integral equals, and let me actually write it a little more to the left. So this integral equals 1 over a squared. So this is its own fraction. And then we've got another one, so x over, and then the square root of x squared plus a squared. And then this is all evaluated from b to a. So in our example, a here is y. A is the constant, and x is the variable. So in our case, x and x, they're both the same thing, and as in this formula here. And y is our constant. So if we just look at this equation, this formula, we end up getting E equals, so our constant stuff out front isn't changing. So now so y is a, so we have 1 over y squared, right? So we have 1 over y squared, and then we have our x. We have x over, let's see, square root of x squared plus y squared, and then evaluated from L to negative L. So, wow, that seems, kind of nasty at first. And then, so you have to sub in your L and your negative L, and we're subbing in for x, remember, that's our variable. So the electric field, k, y, lambda, j hat. And let's see, I just want to make sure I don't make any mistakes. So, nope, looks good. So we're going to get L over y squared, square root of L squared plus y squared, minus, and then we sub in negative L, y squared, square root of, and then we have negative L squared, which just becomes L squared, plus y squared. And so these two are actually the same expression, so we add them, so we end up getting 2 of them. So ky lambda j hat 2L over y squared, square root of L squared plus y squared. And let's see, we can slightly write this little cleaner, so we can cancel these y's. So then we get that the electric field is, we'll bring the 2 out front, and then the L, K, lambda, and then, so 1y cancels, so we're left with this, L squared plus y squared, and then we've got our j hat vector, which I've just sort of took from here and moved over to the right, just multiplied by that. And I want to emphasize, this is an x, this is a lambda, so lambda. And now so we earlier said that because it's uniformly charged, uniform charge density, we have lambda equals dq over dx, which is also equal to q, the total charge of the rod, divided by 2L. 2L is the total length of the charge. So if we just look at this orange equation up here and we take the lambda equals q over 2L bit, so we have lambda equals q over 2L. And so we can solve, we can actually sub in for the lambda over here. So I'm going to need even Whoop, almost running out of space. So we end up subbing this in. So we're just going to literally take this guy and sub it in for lambda. And we get that. And this and you could actually leave the equation in this form if you so chose, but oftentimes they rewrite the charge density in terms of the total charge and the actual length of it. So then subbing that in, you're actually, so the 2's are going to end up canceling, and then the L's are going to end up canceling, right? Because you're going to end up in the numerator, you're going to end up having something like this going on. And then you've got your k lambda, and then you've got everything else that was down here, your y times the square root of L squared plus y squared. And so then these things end up canceling, and you're just left with q in the top. So then you have your k that was there, and then q over y square root of, L squared plus y squared. And in the j hat, let's see if I can clean up the square root a little bit. Square root of L squared plus y squared, and it's in the j hat direction. And so, wow, so this is our equation, right? So certainly a lot of hard work put in there. I also want to, again, emphasize that the total length of the rod is 2L, so the L in this equation is really only half the length of the rod. So L equals one half of the length. So make sure, because that's something that oftentimes you might make a mistake on. So this is for finding the electric field vector at point P due to the charge distribution. And so Q is just a total charge of it. Y is the perpendicular distance from the rod to the point along the y-axis as we drew it. And L is half the length of the rod, and K is Coulomb's constant. And then J is just the unit vector. And so if I went all the way back up here and we wanted to draw the net dE vector, I'll draw it in pink. It would just be something like this, right? Because we got that it was in the j hat direction, so the net vector was along the y-axis. So it was all these vertical components adding up to give this. And again, we didn't integrate. We could integrate this left guy over here if we wanted to, but it's just going to end up becoming 0 because we can visually see that all of the horizontal components, as we go over here and over here, that their horizontal components are going to cancel.